Hi everyone. Thanks so much for joining us on our very first CS Club meeting. Um, my name is Aditya, and I'm here to kickstart the brief introduction the exec team has prepared for you guys today. CS Club is online this year, and on this Discord server, we'll be hosting lessons, having the occasional guest speaker, and overall provide a space for you guys to interact with each other, share your projects, and ask for guidance from us or one of your fellow club members.
All right. Keegan.
Yeah, 1 second.
Technology. All right, sorry, give us 1 second.
Okay, sorry about that delay. I'm Keegan, another member of the exec team. It's nice to see all the.
Wait, oh my gosh,
joined.
I'm sorry, hold on. Oh my gosh,
What?
maybe do that. No, my thing just ended.
Okay, I'll wait.
No, we got this. All right, sorry.
Technical difficulties. Online is posed its challenges that we didn't have before. Let me know when you're good.
Yeah, I'm good. Yeah, sorry. Please go ahead.
I don't see the stream.
I'm on the
That's strange.
meeting, the second slide.
Oh, okay.
Can you guys see the screen?
Oh no. So yeah, I got it. My bad.
Yeah, stream is good for me.
Sorry. I'm
Okay.
As I said, I'm Keegan, another member of the exec team. Our synchronous meetings, like this one, are going to be every Tuesday at 2 p.m., though we might start a few minutes later like we did today. During this time, we're going to have lessons about CS that are about 45 minutes long, and attendance will be taken. At the end of the lesson, everybody who's in one of the voice calls will have the ability to react to a message in the announcement server that will mark your attendance. So make sure you're in the stream, and it should work just fine.
All right, nice. Okay, so I'm doing the next slide. So thanks, Keegan. I'm Michelle, and I'm another one of your execs. And if you guys don't already know, CS Club lessons are split into 2 different rooms. So there's a lesson room and there's a challenge room. So if you're a beginner, don't worry, because in the lesson room, we're teaching everything from scratch from Python. So you can join even if you've never coded before, or if you just know some very, very basic coding and you want to touch up on it, feel free to join us. And the lesson room is also great if you want to get a taste of how the actual computer science courses at SGM are being taught. So if you want to prepare for that beforehand, get a little head start, lesson room is the room for you.
All right. Thanks, Michelle. Hi, guys. If you guys haven't noticed, my name is Kevin. There's a lot of images of me, obviously in the chat. But lesson room sounds too easy for you. We also have a challenge room. Here we cover a variety of topics for people with a bit more coding experience. If you want to preview the topics we'll be covering this year, can be found on the spreadsheet we've sent on Discord in the announcements. If you want a sneak peek on like what our curriculum is looking like, first of all, we'll be delving into more of the theoretical topics, more computer science heavy topics, just to prepare you for some upcoming contests. If you are looking to do that, Waterloo's hosting the CCC computing contest. And then after that, we'll be delving into some more application-based topics such as machine learning, web development, as well as blockchain.
Thanks, Kevin. So
Nice.
my name's Trevor, and I'm here to remind you guys of a few club rules. So first of all, it goes without saying that you have to be respectful, so no harassment allowed. The second rule is to always be willing to help each other out. And everyone here is at a different skill level, so remember to be kind and make people comfortable enough to ask questions. And also, if you haven't already, remember to change your nickname to your first name and last initial, just so that everything's organized.
Yep, nice.
Thanks, Trevor. So, hey guys, I'm Christian, and if you guys have any questions, just in general about anything we said or about how CS Club going to run this year, feel free to unmute or type it out in the questions chat, and I'll be happy to answer them. Yep. So if you have anything, you can type it in questions to make it like.
Oh, feel free to unmute. Yes, we're not that scary.
I actually server muted like I think 2 of you, but
Yeah,
I'll go undo
Sean.
that right now because you weren't muted during the presentation.
I guess it'll take like a minute or two if you guys have any questions. If not, we'll just continue with the rest of the.
Also, if you can't watch the stream with too many viewers, don't worry because after we split up, you can probably watch the streams. And right now, it's just the intro slideshow. So if you just listen to us, that's pretty much all it is. So don't worry if you can stream.
The recording will be on YouTube after the lessons.
Yeah. Also, I just want to mention something, guys. Like, obviously, we're trying to work this format out, so it seems like there's a lot of you guys. We didn't expect this good of a turnout. So later on, if we do have a joint joint lessons or times we need to gather everyone, we'll obviously be looking for a platform that can hold everyone, of course. So don't worry about that in the future. We'll be solving that. And then also something to mention, I guess we mentioned about YouTube. For any of our content that we're going to be doing later on, if you missed something, if you weren't able to come, we'll be posting that to a YouTube channel that we'll be getting to shortly.
And so we had a question from Matthews. He just asked what the requirements for the club credit are. And so I'm pretty sure the standard requirements are just attending more than half of our meetings, I believe. So as long as your attendance is recorded for more than half, we'll see what we can do.
Any other questions?
Alright. If you guys have questions later, just once again, like Christian said, type them out in the voice channel. Sorry, not the voice channel. The questions channel, and then we'll get back to you. Thank you so much, Christian, for answering those questions. I'm Ina. I'm also an exec. Nice to meet everyone. So now that questions are out of the way, we can actually split up into our separate rooms shortly. So if you're listening to Michelle and Kevin, I think, and if you're interested in lesson room, go ahead and join the lesson room voice channel, and where we'll start with an introduction to Python. And if you're interested in challenge room, feel free to join the respective voice channel now and learn about time complexity. We'll take it from here. Thank you guys so much for bearing with us. I know we had some technical difficulties.
Yeah.
We're all figuring things out, so thank you for being part of the learning experience.
Yeah.
So
all right, see you guys in your separate rooms.
Hey guys, so welcome to time complexity. This is gonna be our first lesson in the advanced room. So like Kevin said at the introduction, today's mostly gonna be theory, but we'll get to coding like to next week, I think. So let's get going. All right. So guys, I have a problem. I got a list of 8 numbers that's like 8, 7, 6, 5, 4, 3, 2, and 1. And I need to sort them from the lowest to the highest in as little steps as possible. So I came up with a couple of solutions beforehand, and let's compare them. So the first solution is to first look at the numbers, put the smallest one in the first place, put the second smallest one in the second place, put the third smallest one in the third place, and so on. All right, so that's the first method. Eventually it'll work, right? Method 2 is I shuffle the list. Then I check if it's sorted, and I repeat. And this is just called BOGO sort, and it's not very good. Method 3 is I swap the first and the second numbers. Then I check if the list is sorted. And then I repeat. the steps 1 and 2. And obviously this isn't going to work. So the big ideas here are that an algorithm is a sequence of instructions which is used to solve a problem. And an example of an algorithm in real life would be like baking a cake or ordering bubble tea on Uber Eats. The second big idea is that there's more than one way to solve a problem, like how we had the actual way and how we had the shuffling way. The third idea is that some solutions are better than other solutions, because when you're just randomly shuffling a list, then it's possible that it might not even ever be solved, right? But we know that the first method is confirmed that it will be solved. And the final big idea is that it's possible for solutions to be incorrect, like method number 3, which we just swap the first and the second numbers, and it's never going to finish. So we have a video, and it's just a comparison of a bunch of different sorting algorithms. And it should give us an idea of how some algorithms can be better than others.
Yo,
It's
turn on
nice.
the sound.
We turn on the sound, but it's just like beeping and beep bop.
What kind of music is there?
Good music.
Oh, I don't think you guys can hear it.
I can hear it.
I can hear
Oh,
it.
you can? Oh, Just
Lower the volume a little bit.
it's okay, I'll just keep it muted. What's important is that we see that some sorting algorithms finish before others. It's pretty cool. It's a visual way of understanding how sorting is good. Okay, I think that's enough. You get the idea, right? So the definition of computer science, well, on Wikipedia, it says that computer science is the study of computation and information. And a very important part of computer science is the analysis and creation of efficient algorithms in terms of both time and space. Okay, Aditya.
Okay, 1 minute. Okay. Hey guys, I'm going to be talking about program analysis, and it's kind of an important topic as we move on to CS Club. So you guys should. It's a fun topic. You'll get it. Go to the next slide. Okay. So firstly, what is program analysis? And program analysis is the process of automatically analyzing the behavior of computer programs. So basically, we're trying to find out the unique characteristics of each program and kind of find the similarities and differences between two programs. And after you analyze a program, that gives you whether or not it's fast, slow, correct, wrong, and all these different like factors. Okay, Trevor, press. So program analysis is split into multitude of things, but I want to talk about performance and how algorithms can be faster than they think they are, and how to properly compare algorithms. So go to the next slide. So what is performance analysis, or how do we analyze performance for an algorithm? So there are four main factors that influence performance, and that's maintainability, security, modularity, and speed. And here, the first three are really software orientated. So that's for more like applications. So like you want to make sure an application is secure so you don't leak important information. So um, scalability of a program really depends on its performance. So if you're actually creating a large program like Zoom, let's say, um, you want to make sure it's scalable so you can host up to like 50 people, or it's not going to work for 50 people, then like the performance really affects the scalability of a program. And if it works for one person or one concurrent user, that doesn't mean it's going to work for multiple people. And so that's why we kind of analyze performance, because if we can find how fast an algorithm goes, or how like secure it is, then it'll actually help us like find out if we should use use this software over another. So for example, if Discord can't have 50 people on it at once, but Zoom can, and that's the problem we're going against, you can see how Zoom is built better. Go to the next slide. And this kind of showcases a question that's going to segue into the next slide, but I'm going to give some backstory to it. So you're given a problem and you need to write some code to solve it on your machine. And you basically want to challenge your friend and see if they can write an algorithm that's better than yours. How do we find out that mine is better than Trevor's? This is an important question because this kind of tells us if an application or a program really is as fast as we think it is. So go to the next slide. If me and Trevor were to solve a problem and we wanted to find out which one is faster, I think the first thing a beginner in programming or someone who just has small experience in programming would think, I take a stopwatch and I run the program and I see which one takes less time. And time here is being measured in seconds. It's a universal time, a universal unit. And there are a lot of problems with this, right? Because go to the next slide. There are a lot of problems with this. So these are just some hurdles that you'll come across if you try in solving this problem this specific way. So firstly, if you have different inputs, that will kind of change the way the algorithm could run. So for example, if I entered a bunch of strings, um, a bunch of characters for like one input and then a single character for another one, that might change the algorithm. It might not, but it might, and that's something we can't take the risk of. So um, those variables we can't kind of control. And secondly, processor speeds. So my my laptop might be super slow compared to Trevor's. And then when you're comparing these two programs, then you might see which one is faster, which one's slower. And you might be saying, okay, what happens if I enter the same input and I put it on the same laptop and I time them differently? So I first do Trevor's, it goes for like couple X seconds, and then I do mine, it goes for Y seconds. But there's another problem here, and that is there are a lot of languages or tools that we can use to write these algorithms. So I could solve my problem in C++, and Trevor could write his in Python. And C++ is faster than Python, and that's kind of going to defeat the purpose of finding which one's faster. Because if I do it in C++ and it's super inefficient, and Trevor does it in Python and is as efficient as it can be, and mine's still faster, then like we're not going anywhere, right? So this is click and this kind of introduces theoretical analysis on algorithms. So we cannot trust seconds because there can be human error or like human fault, and there's obviously languages and other hurdles. So what is theoretical analysis, right? Like why, like what even is it? It sounds like a big word that no one ever uses it. But it's basically saying that we, instead of timing an actual algorithm, we just kind of look in the algorithm and analyze the performance and analyze the program and try and count how much time it takes. And this might be weird. How are we going to count it if we're not going to use seconds as our unit of time, right? But there's something called the frequency count method, and I've been introduced to it, and it's kind of helpful for beginners. And the way it works is basically I you're given you're given pieces of a code base, and you basically want to go through each line. Each line you just want to go through and see how much time each line will take. And there's certain base cases. So like if I'm assigning a variable, it's going to take 1 unit of time. If I'm returning a variable, it's going to take 1 unit of time. If I'm in a for loop, it's going to run n times, and we'll see that in the next slide. I'm going to go through some examples, and this will help you. I'm pretty sure examples are a good idea. Click again. Okay, so we're given a problem. We want to get the product of all the elements in an array. Okay, it's simple, right? You basically loop through the array, and then you multiply the previous one to the one that we have to meet. So on line 2, you can see that we assigned a variable called sumo. We just named it 1 or assigned it to 1. The time that it takes for this to assign this variable is going to be 1 unit of time. And here comes kind of the important part of the lesson, and that's the for loop. On line number 3, you can see that we're going for I in range 0 to n, and then colon, and then we indent, and then we just keep going. I want to talk about what happens on line 3. So what the line is saying is that we start from 0, I is equal to 0, and we want to go all the way till I becomes greater than n. So we want to just keep iterating through I, so 0 to 1 to 3 to 4, all the way up to n. And this kind of creates a loop, right? And this loop is going to run like n times. So when you see the colon and you indent, you know that obviously sumo is equal, or line number 4 is going to repeat n times. But what you don't know is that line 3 will also repeat multiple times. Usually in a for loop, we're introduced it so everything inside a for loop is just going to keep repeating until it goes from 0 to n. But that's actually not the case, because you go from 3, you go to line 3, you go to line 4, and then after you go to line 4, you go back to line 3. And this kind of like goes back and forth. And what's happening in this back and forth motion is I is getting incremented by 1. Every single time I gets incremented by 1, we're checking that is I greater than n. And if I isn't greater than n, we just keep going. And once we get to a case where I is greater than n, and that's when I is equal to n plus 1. And that's when we find out that line 3 is going to run n plus 1 times. It might be confusing, but I can answer any questions after. And so we move on to line 4, and its assignment. So we're doing sumo is equal to sumo times r in index I, and that usually takes 1 unit of time. We take that whole line out of context, you'll tell me that it'll take 1 unit of time. And since it is in a for loop, it's going to run n times, so that's going to be n times 1. And finally, on line number 5, we're returning a value here, and that's going to take 1 unit of time again. We add everything up, and we get 2n plus 3. That is the total time spent on this program. The important part of this is not 2n plus 3. It's the degree of this polynomial. Trevor will get into it later, but I want you guys to keep that in the back of your head. 2n plus 3 is what we see, but you'll see that it's not always about the polynomial. Okay, second example. It's kind of the same one as the last one, but I just kind of wanted to do it so we can kind of get used to it. So don't worry about line number 2. We're just going to go from line number 4, and you can see it's a for loop. It's going to 0 to n. And like I said before, line of number 4 is going to go n plus 1 times because it's looping, right? It's going to go everything inside the for loop and then go back to the for loop line. And it's going to keep doing that until I is greater than n. And that's when I is greater than is n plus 1. So that line is going to run n plus 1 times. We get that. And then line number 5 is another for loop that's nested in the previous for loop. And we know by principle now that a for loop that's arranged like that specific structure, is going to be n plus 1 times. But line number 5 is in line number 4. So that means how many times n is, it's going to repeat line number 5's for loop n times. So we're kind of multiplying the for loop. So if you look on the right side of line number 5, I did n times n plus 1. That's because we knew n plus 1 was going to be the time for that for loop. And a good way I like to kind of find out how much time a for loop takes is I take it out of context. I just take that line out of context and I just see, okay, if I just look at line number 5, it's going to take n plus 1 times. And since it's in a for loop, it's going to run n times because it's wrapped around it. And we kind of do that for line number 4 and 5. And then line number 6, it's assignment, right? So we're doing z indice ij is equal to blah, blah, blah. And that usually takes 1 unit of time. We take that out of context, it'll take 1 unit of time. But it's wrapped in 4j in range. And we know 4j in range, everything inside it will repeat n times. Okay, so it's going to run n times 1 times. Okay, but on line number 4, for I in range is still looping around. So that means it's going to run n times 1 times. So that's going to be n squared. And On line number 7, you can see that we just return it, and that's going to take time 1, 1 unit of time. Add everything up, we get 2n squared plus 2n plus 2. And like I said before, we only care about the degree. So you see the degree is 2 here, right? Just keep that in the back of your head. It's really important. It doesn't matter if 2n or it's 4n or it's like 2n plus 5, 2n plus 100. It just doesn't matter. It just depends on n. N is the dependent variable here. Go to the next slide. Okay, so the frequency count method was kind of made sense. If you didn't make sense, then like I can talk about it more. But it's basically we count everything that happens on a specific line. Some key takeaways is that everything inside a for loop usually will run n times unless specified otherwise, or if you actually look into the program. There is another method that I know that can kind of like, it's for like when you're doing recursion and stuff. So if your for loop is running more than, what do you call, 0 to n, it's running to like n divided by something, then it'll run for a specific time case, but that's for another time. So everything inside it will run n times. And always remember that assignment variables, comparative statements, returns will always take 1 unit of time. And this kind of leads us to computational complexity. So everything I told you guys before that was like fn is equal to 2n squared plus 2n plus 2, like the conclusion we got at the program, that means something, right? What do we do with that? And not everybody in the world is introduced to that specific notation. It's just a wild notation, right? And so that's where we get into something called big O notation, and Trevor will get into it more.
All right, guys. So for the next couple of slides, we'll be talking about computational complexity, which is a bunch of theory. That's not boring, actually. So here's just a definition of computational complexity. Basically, what it is that it's the amount of resources needed to run an algorithm. And usually it's described using time. So in other words, that's just the amount of time you need to complete an algorithm. All right, so just some review. What this here is, if you guys can see my mouse, the f of x, that's what's called a function. And what a function does is that it takes an input and maps to one output. And here I'm talking about a mathematical function. So not like one of those programming ones. Whoops, I'm getting a phone call. Sorry, guys. Maybe I should ignore that. So, for example, for f of x is equal to x squared, we have f of 1 would be equal to 1 squared, and f of 2 would be equal to 2 squared, and etc. So, it's probably really distracting. All right, sorry, guys. I'll mute and be right back. Hi, really sorry about that. So, back now. Basically what it is that it's just like an equation of y and x, where f of x just replaces the y, and we only focus on what x is. And what asymptotic growth behavior is the rate at which f of x grows as x approaches infinity. And that's just when x becomes large. So like when x is 10 trillion, 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 trillion. So here's an example. For f of x is equal to x, and g of x is equal to x squared, we can clearly tell that g of x grows way faster than f of x, right? Because for f of 10, x is just equal to 10. And for g of 10, x is equal to 100, because 10 squared is equal to 100. So I'm going to say something else here, which is that if f of x is equal to c of x, where c can be any number, so c could even be 10 trillion, and g of x is equal to x squared, g of x will still be growing faster than f of x eventually. And the reason why it's like this is because if you took x is equal to 10 trillion, then you would have f of x, 10 trillion plus 1, sorry. You took x is equal to 10 trillion plus 1, then f of x would be 10 trillion times 10 trillion plus 1. And g of x would be 10 trillion plus 1 times 10 trillion plus 1. So we can tell that eventually g of x will start growing faster than f of x. And for example 2 here, we have a function f of x is equal to x squared plus x. And what I'm going to say here is that eventually x will become negligible compared to x squared. And we can think about this if we say we take x is equal to 1 trillion. And obviously 1 trillion squared is a lot bigger than 1 trillion. So much bigger that we can just ignore the 1 trillion altogether. And what we say here is that x squared plus x is asymptotically equivalent to x squared. And what asymptotic means is that it's like when things approach a value. And here in this case, it's like when x is approaching infinity. All right. So here's another term, here's another definition, and that's order of growth. And what that is, it's just a set of functions which are asymptotically equivalent. And here's some examples in this table. So for the order c, which is a constant, we can have functions that are 1, 2, 5, and 12,828. And what these are, they're just horizontal lines, right? So eventually, if we zoom out enough on like a graph, then they'll eventually look like they're the same. And then we have log base b of x, x log base b of x squared, x cubed, and c of x. And this is in order of speed. So c grows the slowest, and c to the x grows the fastest. So we can express the number of steps needed to run an algorithm as a function of n, as like a mathematical function. This is where Aditya got the f of n from. So we take n as the size of the algorithm's input. So say we wanted to sort a list that had a size of n. So the list could be 3 elements long, or it could be 10 elements long, or it could be 100 elements long. So let's call this function f of n. The asymptotic time complexity of an algorithm is the order of growth of f of n for that algorithm. Right. And the reason why this is the case is because computer scientists care about how well computers can handle larger and larger inputs. And now we're just going to get into some notation, which is big O, big theta, the symbol means theta, and big omega, and this symbol means omega. So O, theta, and omega are 3 symbols used to classify algorithms based on their asymptotic complexity. And the reason why we have 3 of these is because algorithms can have variable running times. And Aditya mentioned this before. So say we had a sorting algorithm on a list that's already sorted versus a sorting algorithm on a list that's not sorted. Well, obviously, the list is already sorted, so the sorting algorithm doesn't have to do anything, which means that this first case is going to take way less time than the second case, because the second case you actually have to do work. So in general, we can think about O as being the worst case, omega is the best case, and theta is every case. All right, so now we're going to go into more detail about big theta, big O, and big omega. So this is the math definition that I ripped out of a textbook. And basically, a function f of n is theta of g of n if there exists 2 constants c of 1, c2, such that c1 multiplied by g of n is less than or equal to blah, 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 f of n less than or equal to c2 multiplied by g of n for every n which is greater than some number n0. And the English translation of that is that f of n is theta of g of n if f of n and g of n are asymptotically equivalent. So say we had 2 of x, a function 2x plus 3. And 2x plus 3, we say that that is asymptotically equivalent to x. So 2x plus 3 is theta of x. Well, in this case, we won't use x, we would use n. Big O is really similar, except instead of having a lower bound, instead of having that lower bound on f of n, we have only an upper bound. And I'm going to skip the math definition for now, but what O of g of n is that a function f of n is O of g of n if the growth rate of f of n is less than or equal to the growth rate of g of n. So technically, it would be right if we said that a function f of x is equal to 1 is O of x squared. And what big O notation is used for is that it's used to represent the worst case running time of an algorithm. So it's the upper bound of the time it takes. And the last one we'll talk about is big omega. And big omega is the opposite of big O. So a function is omega of g of n if the growth rate of that function is greater than or equal to the growth rate of g of n. So g of n would be the lower bound of what that function can be equal to. And what g of n is used as the best case running time of an algorithm. And I don't think it's used very often. The most popular one is big O, because we only care about the worst case. We could go through some examples at the end, but we do have a big announcement, which is a CS Club project. And the project will be holding 2 competitions with prizes throughout the year. And you guys have a chance to submit and present a project for a chance to win prizes. So the start date is today. So you guys can get started working on this project right after this meeting. And the presentation date will be the meeting right after the end of winter break. And that's also the project deadline. Right. So Aditya, did you want to go through some examples?
Do we have time?
What if we had a vote? How about that?
It's up to them, honestly.
Vote. I typed a message into the chat, and I'm gonna try to react to it. Here we go. Eyes if you want to, and thumbs down if you don't want to. It looks like the majority is going to be examples. Okay, crab, C, R, T, M, lobster. Nice. All right, let's go through some examples then. Here, I'll stop streaming now and I'll switch screens. Oof. All right. Do you actually want to make a collaborative REPL?
I can.
Don't use that. REPL dot it
It's loading.
slash languages slash Python 3. Oh, I'm not logged in. Whatever. I'll just share this. Screen. Live. We are back live. Hello.
Yo, share me this.
Maybe I should sign in. Okay. Yeah, I should probably sign in and share with Aditya. Okay, we'll be right back promptly. Let's see if I can remember my REPL.it account password, which I think, okay, safe. Aditya, what's your REPL?
That's my name. Like, full name. Yeah, DM it to you.
Oh, found it. We're back. My credit card number? Wait, let me find it. 330
Wait, my
4 5757 8 9 10. Wait, crap, I said 10. No. Are you in, Aditya?
I'm loading.
All right, good. Let's go with a simple. How about O of n? How about an O of 1 algorithm? Check this out. So this one is going to be O of 1. Here it is. All right, you guys ready? Whoa.
Oh.
1 plus 1. This algorithm is O of 1. And 1 just means constant.
Yeah.
Because it only takes 1 step to compute 1 plus 1, right?
Yeah. I'll do O of n. This is not in order, by the way.
We're just doing random ones that we'll think will
Yeah.
be helpful. So range on. Let's just say
Yeah.
n can be anything we want in there.
E.
O of n squared. All the polynomial ones can be expressed as nested for loops. So let's say O of n squared would be the same thing. We loop like this, and then another for loop inside for j in range n. Let's do, yeah. Which one's a spicy one we can do? Do you remember the Fibonacci one? That's like O of what?
N factorial?
O of something to the x, O of something to the n.
Wait, is it 2?
It's recursive, right?
It can be, yeah.
Yeah, we're just doing random ones. I think 2 more examples will do. How about we do a O of okay, I think we'll just do one more. I'm not even sure if it's 2 of them, but I think it is.
I think it is.
Fibonacci.
Yeah.
Then you have the nth Fibonacci number. Then you go like if 0 return. So return 1. It was. Else return Fibonacci of n minus
1 plus past 2.
plus Fibonacci n minus 2. So like that.
Yeah,
I
basically.
think it was. And this one has the time complexity O2 of n. Actually, wait, hold up. The next one, the one that we talked about before in the first example, this one is, okay, last example, I promise. This is O of n factorial. And this is like really bad. Like you guys don't want O of n factorial. What we do is we import random and we have that list. 8, 7, 6, 5, 4, 3, 2, 1. And then just while list, let's pretend there's a function called is not sorted list dot wait, is it a random dot shuffle list print list. All right, guys, I think that's probably all the examples we need to go through. If you guys have any questions or concerns about anything we went through, feel free to send a message into the challenge room chat. Overvlog again.
Hey, so just a quick announcement about attendance. It sounds like the lesson's almost wrapping up. Don't leave the stream quite yet. You have to be in the stream to have your attendance marked. Lesson room all left, so I have to see if I can get as many of them back as I can. Just bear with us, please.
Yo asks, why is Fibonacci example 1 2 to the n? And the reason why we know it's exponential, which is 2 to the n, is because we would do something where we would like split up all the function calls into like a tree kinda and count all of them at the end at the bottom. But it's kind of weird. And just like take my word that it's that it's exponential. Just trust me on this, even though I might be wrong. Yeah, what Christian sent. And then if you eventually just like count all those fibs at the bottom, I guess the examples are over, so we can end stream. Oh wait, hold up. Attendance. Machine learning for self-driving. Yes, we're gonna be doing machine learning. I think after March break.
Yeah, I think we're starting off with the content that we're doing. We're starting off with more of the theoretical computer science content to get you ready for. There's a lot of people who want to write the CCC, the computing contest that I mentioned. It's a competitive programming contest held by UW. That contest directly impacts your application. That's why a lot of people want to write it. So we're preparing you with the more theoretical competitive programming concepts. And then also you'll be answering like you'll need all these concepts and tools in technical interviews when you're applying for a job. They really like to have these type of interviews. But later on, we'll be, of course, after that, we'll be going into more of the application-based fun stuff, including, like I said, machine learning. We'll be doing 3 lessons, I believe, on that, on the concepts as well as coding with you guys, one step at a time. I'll also be doing some web development stuff, just teaching you guys about programming tools as well, some of the tools that we like to use, and then also being able to do some other topic like I think blockchain, and then some other fun stuff in between.
Fun stuff.
Of course, you guys can check the schedule. I believe I don't know if we have this posted, but we're planning on posting an Excel sheet. It includes all of our lesson plans and what we're planning on doing.
Yeah, it's in the welcome message channel if you guys want to see. Yeah, so computer science involves I'm pretty sure computer science is like a subset, a branch of math, right? So
Yeah.
before we get into a bunch of cool coding, we'll be doing a bunch of math too, which isn't bad. Next week we're doing C++, right? I think. I'll need to check.
The reason this lesson we went over, I guess, using Python to show you guys the more conceptual parts of computer science. And if you guys want to know, computer science actually was like a lot of the research that's done was done in the 80s when we didn't even have the programming to do it. And now, right now, we have the hardware now, so we're able to use that to be able to catch up. But yeah, a lot of this is theoretical, I guess, and we're using next week. I believe we're using the reason why we mentioned C++ is because there's some lower level concepts that we need to teach you guys through that programming language because it introduces some more. You can be a lot more specific with things such as memory. Yeah.
All right, guys. So attendance is already up. So meeting's dismissed now. I'm gonna end the stream. You guys can stick around if you want to talk.
If you
or have any questions.